It's time to talk about nuclear testing. And I'm going to begin by talking about the safest and least contaminating form of nuclear testing, which is underground testing. Now, there are two varieties of underground testing. They're both carried out by the United States in the same area, which is in Nevada, not too far from Las Vegas. The Nevada test site has several areas that have been used. There are a couple of flat areas, in particular called Frenchman Flat and Yucca Flat. And then there is a pair of mesas at the north end of the test area, which have mountains into which are drilled tunnels, horizontal tunnels. We'll talk about that next. But for today, let's talk about vertical tunnels. What happens when a nuclear weapon or nuclear device is detonated at the bottom of a vertical tunnel is that it forms a bubble. It vaporizes the rock and the water in the rock, and it begins a fragmenting procedure in which the rocks around the bubble are broken up by a series of fractures. Part of the rock in the bubble is actually liquefied, and it collects at the bottom of the bubble as a puddle of glassy material, highly radioactive. 1 week after the test, another hole is drilled at an angle in order to sample the material, the glassy material at the bottom of the cavity produced. This glassy material is still molten 1 week after the test. Over a period of time, which varies from hours to weeks, the rock around the cavity, which has been weakened by the explosion, begins to break up and to fall into the bottom of the cavity. This causes what appears to be a vertically rising bubble of empty space surrounded by broken up rock. And eventually this rock reaches the surface and gives rise to what's called a subsidence crater. Now, in order to prevent a lot of radioactive material from going up the drill hole, which was used to lower the bomb into the cavity in the first place, a procedure called stemming is used. This is a stemming plan used by one of our nuclear laboratories, the one at Livermore. Basically, after the bomb is emplaced, the hole it was dropped down is filled with gravel. But every once in a while, in this gravel hole, they put in a layer of fine sand and pour in concrete. In this example, we're showing 6 concrete plugs. They also have to take care to seal the area around the cables, the test cables, which lead from the instruments above the bomb to the trailer park of recording devices up on the surface. I looked on the internet to find examples of the instrument canisters that are lowered into these vertical shafts, but I couldn't find any. However, when I had been at Los Alamos, I did see such an instrument canister in the library and museum there at Los Alamos. So I got in touch with the librarian, the head of the museum, and asked him to take some pictures. And these are a couple of the pictures. You can see there are pipes. This whole white thing is an instrument canister, and the bomb itself goes at the bottom. We'll see that in the next picture. All these pipes lead up to instruments which have to function within a microsecond of the explosion. So basically, the instruments are watching the explosion. When the explosion takes place, the radiation, the light and X-rays and gamma rays, travel quickly up these tubes, which will be evacuated. There's nothing in them. And at the top of the tubes are the instruments which measure the amount and quality of the light. And then there are other tubes which will measure neutrons coming out of the bomb. And all of these instruments are about to be vaporized. They have to carry out their function in life in a time of about 1 microsecond, because after that they won't be there anymore. So they measure the radiation, they translate it into a digital signal, and send it up the cable to the trailer park on the surface. These instruments are not just run-of-the-mill scientific instruments. These have to be extremely expensive, very high-speed instruments, and they cost millions of dollars for each test. The particular test whose tower I visited contained $53 million worth of instruments. Now at the bottom of the test canister is the nuclear device itself and the timing and firing equipment for the device. This stuff is at the bottom because the instruments have to be higher than that so that their signals can go up the cables toward the surface. If we look at the process of lowering the test canister down into the vertical shaft, what we'll see is something that looks like about a 5-story tall white building with cranes suspending the test canister above the shaft and a lot of cables on the desert floor. There is enough cable here to go all the way down the, say in this case maybe 1,200 feet to where the bomb will be emplaced. And the lowering of the test canister takes a long time because they have to carefully feed these cables down along the steel cable that suspends the bomb and the test canister. So it can take a week to very slowly send all this stuff down the shaft until it's deep enough. The next picture here shows the same procedure but from a different point of view. We're looking down on it now from above. We see that white building on the right. That is where the hole has been drilled, and the crane is lowering it down, and you see there's still a bit of cabling left on the desert floor. And over there on the left, you see the trailer park is what they call it. It's a bunch of trailers full of instruments that are recording the information that comes up the cable from the bomb. There have been a lot of tests like this at the Nevada nuclear test site, and here is a portion of Yucca Flat, and every one of those craters you see is a subsidence crater from the collapse of the rock above the nuclear test. These are not actually nuclear craters. These are craters on the surface more than 1,000 feet from the position of the bombs underneath the surface. But the size of each crater gives you some indication of the amount of energy released in each bomb. This table shows how much radioactive material has been released from tests at this site. This table is in an interesting unit called the Curie. A Curie is approximately the radioactivity in 1 gram of radium. So some of these tests release almost nothing, like this one called Hybla Gold in 1977 was 0.005 curies, and others are sort of accidents. For instance, Mighty Oak, 1986, released 36,000 curie. That is a phenomenal amount of radioactivity. But if you look below this, you'll see the really serious ones, like, for instance, Bainbury, 1970, released 6.7 million curies. And if you look at all of the atmospheric testing at the Nevada site, you can see that from 1951 to 63, 12 billion curies of radiation was released into the atmosphere. If we look at the distribution of radioactive fallout across the United States, we can see that there's some originating in southern Nevada, second state from the left there, and extending over into Utah and beyond that. But you'll see that the hottest spot on this map is in Idaho. Now, why is that? They didn't do any bomb testing in Idaho. Well, it's because they did the reactor testing in Idaho, and there were some pretty serious accidents there. Plus, they tested some very dirty reactors like the ones that were going to be used in nuclear airplane engines, which turned out to be altogether impractical. So the upper U.S. got quite a dose of radiation, but it wasn't from bomb tests. It was from reactor tests.